software that most of you know. I'm also a creator of the ZeroDay Engineering project, creating specialized training courses about vulnerability research and reverse engineering. And I'm a winner of on competitions. I also happen to spend quite a lot of time here in Thailand, and it's great to see that security conferences are finally coming here. So I think there should be live stream to Russia. So I want to say hi to my Russian fans. Because last year I came to Positive Hack Days and it was such a great experience. So let's get into it. This talk is going to be a continuation for those who are not familiar with my work. I started this series of talks about state of the art focusing on specific softwares in 2020. So there was a talk about hypervisors and virtualization vulnerability research in 2020. Here I linked the video recording of it on my YouTube that you can click if this topic resonates with you. And this is going to be basically the same template. So what I'm going to do is I'm trying to cover big extremes of our subject area. First, I'm looking at the big picture of what the topic is about, the attack surface and so on. And then I'm looking at deep technical details of specific vulnerabilities or exploits to do the deep dive. I think there is some problem with the mic. So the plan. Today, my plan was to zoom into this topic from the big perspective of cybersecurity. I think it will be very appropriate because people often ask me, because in this kind of technical presentations, normally I go straight into the technical details because I'm deep in this industry and I'm really sometimes not aware of that some people, they don't get how do we get there and how does it relate to other parts of the industry. So today, the people asked me to do that, and today I really wanted to zoom into this, starting from the really, really big picture of the cybersecurity industry, passing through the big picture of JavaScript engines, the system internals, and attack surfaces, and finally ending with a deep dive into specific technical vulnerabilities that can be exploited in JavaScript engines. So I will do my best to really connect everything together. So even if you are really just entering this industry, I hope you will be able to benefit from this talk and really understand what's going on here. If it doesn't work, please do reach out and I will be happy to explain because I'm working on trainings for beginners. So your feedback will be really helpful for that. I think this plan is a bit not realistic because I have like 45 minutes, including questions, 10 minutes per each part. So I'm going to really focus only on the key points. And also I will give you a lot of pointers for further research, reading, watching, or related materials that you can dive into a specific topic that resonates with you. So here is my paradigm of cybersecurity. This is a simple functional model which represents everything that's going on in the industry. This is a security conference. So I'm assuming that everybody who is here in this audience is working somewhere in here. You can find yourself somewhere. The basic idea here is that rectangles represent sets of knowledge and skills or specializations as we think about them. So when you're just entering the industry, everything looks a bit disconnected. Maybe you see penetration testing, software security assessment, offensive security, vulnerability research, and everything is so disparate. So what I want to show here is that these areas are really not disconnected at all. First, they share a very common core of knowledge and skill. And secondarily, they not only share a common core, but also they are kind of systematically related to each other. They're hierarchically organized, and there is a system how they all connect to each other. And this diagram shows it. There is a lot going on here, even though it's just a draft. I'm not going to go deep into it because it's not the main topic. I did a free webinar about this topic, which it's not listed anywhere on my website, but you can reach out to ZeroDay Training in Twitter and we'll send you the link to this webinar if you're interested in this more kind of high-level perspective. For the purpose of this talk, I want to highlight just a few key points that are related to vulnerability research. Point number one, you can see on this diagram, it's separated into parts, the defensive side and the offensive side. So I think this is not obvious to many that defensive and offensive knowledge and skills are basically related to each other, and they are based on the same core set of knowledge and skills. That is why their rectangles are the same. So whether you're finding vulnerabilities or patching them, whether you are doing penetration testing or working on the defense side to develop software, you kind of work with the same compact internal core sets of skill and knowledge. This I think is not very obvious, but I think that some people started to realize that, because in my trainings that I do, I see that I'm doing specialized trainings about vulnerability research, super specialized and niche. And I'm seeing that people are coming who are not really, it's specialized for security researchers, for professional ones who want to participate in competitions and so on. And I'm seeing people coming from really different industries, penetration testers, software developers, even managers. So these people, they start to realize how it works. What I'm trying to show in this diagram, that the subset of skills that you'll be using is actually the same for defensive and offensive side, if you're kind of looking deep enough. So this is the first part. The second point of this diagram is that vulnerability research, software vulnerability, technical and social vulnerabilities lie at the core of this diagram. It is the heart of the entire industry. This also, based on my conversations with people, it seems like not really obvious to some people, because vulnerability research sometimes can be thought about as a distinct specialization, but in fact, it's like the core of entire industry. What I want to show here, so this is basically the same model, but shown at a different angle. Here, I show the vulnerability research as a foundation of the whole thing. Consider that no matter what you do, it all comes down to vulnerabilities. There are two types of vulnerabilities: in technical software or hardware, and in social systems, in humans and businesses. And that's it. Any cybersecurity compromise, anything that's going on in the industry comes down to vulnerabilities. What happens if you take out this bottom layer? The whole diagram falls apart. If there is no vulnerability, there is nothing to defend from, there are no exploits, the Trojan cannot get into the system, there is no need for cyber detection agents, for some kind of compliance, for cybersecurity budget, nothing, just the industry stops to exist. Now, why I'm saying this is not to represent my specialization like a kind of holy grail of the whole industry or something like that. Well, it may be. In the end, what I mean to say is that because of how we clearly see it here, vulnerability is the foundation. So regardless of where you work in the industry, the knowledge about system vulnerabilities is crucial to you. It's crucial to your skill set. And the better you know this, the better skill set you have around vulnerabilities and exploitation, the better you will be able to perform at your job, and the better you will be paid. So there is very straightforward logic here, although I think it's not very obvious. It means that regardless where you're working, maybe in penetration testing, software assessment, some kind of defensive developments, really even just software developer, the vulnerability skills and knowledge is absolutely fundamental to what you do. And the sooner you realize that, the faster you will be growing in your career and the better profits you will be getting. Also, it kind of implies that vulnerability research and vulnerabilities themselves, as it can be clearly shown here, they possess some kind of intrinsic value. And in fact, this value can be observed in market pricings, in job proposals, in how in various opportunities of making money in this industry. So vulnerabilities can be sold for bug bounties. Many software developers have their own vulnerability research programs, bug bounty programs, where you can submit a bug and they will pay to you. You can also get a job as a vulnerability researcher. You can work on the gray or even on the black market if that's your thing. It doesn't matter to me personally. What I meant to say is that vulnerability knowledge is kind of really like the heart of this whole thing. It represents a certain intrinsic value, And it really is crucial. If we take out vulnerabilities, if they don't exist, then the whole industry just falls apart. Now, what I will do next is zoom into the center of this diagram. For now, I'm not looking at the other rectangles that represent various aspects of cybersecurity compromises and defenses. I'm just going to zoom into the vulnerability and exploit mitigations. What is in there, inside the vulnerability research industry? There are two types of things. Roughly, we can separate all the knowledge and skills in vulnerability research in two classes: the universal knowledge and skills and specialized knowledge and skills. There is also a bit of confusion here. Universal knowledge, things like general fuzzing, general reverse engineering, CPU architecture, once again, general, low-level debugging, knowing how to use them, some sort of hardware theory, vulnerability theory. All these things are important, but it's the specialized knowledge that gets you the job done. It is the specialized knowledge that allows you actually to find valuable vulnerabilities. So these two parts of the skill set play together. And actually there is, it's not like two extremes, but there is a certain spectrum, which I am simplifying to show only the two extreme parts. So basically you will need both. Specialized knowledge and skills is what actually gets your job done, is what makes you valuable on the professional market at the most basic level of it. And universal knowledge and skills is something which enables knowledge transfer, it gives you deeper insight, and it actually the thing that gives you the edge. So if you're considering you're competing with somebody, both of you know very good some sort of specialized knowledge, like attacking a specific browser, then the one who has the more universal knowledge will have more deeper insights and will be better performing at finding vulnerabilities. Next, I'm zooming into one particular area of specialized knowledge, which is browsers, getting closer to my today's topic. Web browsers, it is probably the most crucial in terms of cybersecurity because browsers are used by everyone. They're used on on all sorts of devices, both mobile and desktop devices. And really, a lot of compromises happen through browsers, especially the high-end ZeroDay attacks targeting high-value targets. Inside of the browser, there is a JavaScript engine, which enables execution of JavaScript. Here you see that the two ellipses intersect because the JavaScript engine is not like fully contained inside the browser. It's actually a standalone system which can be taken out, built separately, and in fact it can be embedded separately in other software, which is what commonly happens. So this is why I'm discussing JavaScript engines separately. It's a really standalone entity. Here is the same diagram with a bit more detail. The thing that I've drawn here, the outer ellipse represents embedders. What is an embedder? Probably not all of you in this audience are aware that browsers and JavaScript engines actually power a huge amount of software that we all use. For example, Google Chrome with V8 JavaScript engine powers Node.js. Node.js in turn powers Electron framework, and Electron framework powers everything like Discord, Signal, whatever, Skype, many software that you use every day. It means that, at least in theory, if we're attacking browsers, we're attacking all this huge amount of software. This is the theory. In practice, it's a bit more complicated because the attack surface sometimes is not reachable. But anyway, this is something that has to be considered. Also on this diagram, I'm showing a little bit of details about the attack surfaces in browsers and JavaScript engines. So on the browser side, there is the various subcomponents, such as document object model, the media, the sandbox, and JavaScript is one of these attack surfaces. Inside the JavaScript engine itself, also there are different attack surfaces that we can attack to find the vulnerabilities. Now, moving on to our JavaScript engines. Here is the same thing that I showed on the previous slide with a bit more details. This is the attack surface of browsers and JavaScript engines. it's not complete. It's just to give you an idea of how it all works. So in the browser, we have all these different subsystems that can be separately attacked remotely. And one of them is JavaScript engine. The JavaScript engine itself is a very complex and standalone thing that has a lot of attack surfaces in its own. In order to even begin to understand the internals of a JavaScript engine, you will need basically two pieces of JavaScript theory. The first piece is ECMAScript specification, which is the technical specification that defines how JavaScript language is, how it works basically on all levels. And the second piece of information theory is compiler theory. For that purpose, I'm linking here a photo of the book on compilers, which is considered de facto standard in it. Because underneath, JavaScript engines are just compilers. And they're really the most advanced compilers that you can find nowadays. A few words about the ECMAScript specification, just to give you an idea of how it looks like. So it's a technical spec. It's rather large. It's split into different sections. And it defines how the language is structured, how it defines the syntax and semantics of the JavaScript language itself, but also it defines internal functional characteristics of the language, such as abstract operations, what can be done. It defines the objects and the fundamental primitives of the runtime itself. It defines the common runtime operations, and it defines even things like it tries to define memory management. There is not much about it, but it kind of mentions it about the garbage collection and so on. The abstract operations in the spec is actually the functional specification of what is going on inside the JavaScript engine at an abstract level. So the spec defines this as an abstract level, and JavaScript engines then implement this in the code. It means that this is important because if you want to look at the code of JavaScript engines, then the most basic thing that you need to do is read the specification, and you can map some of these abstract operations directly to JavaScript code. So after reading the spec, you will be immediately familiar with a large part of the source code of any JavaScript engine that you want to look at by simply mapping it back and forth. Also, in the code itself, there will be much more developed code, and it will have a lot of additional details that the specification does not define at all. For the ECMAScript spec, I will leave it here because there is a lot to talk about and it's not our topic for today. There is a link. I have a masterclass about JavaScript engines hacking that includes like a really deep dive into both the spec and all the essential theory and practice that is needed here to attack JavaScript engines. Meanwhile, I want to move on to the more practical topic, which is the JavaScript engine execution pipeline. This is an example of JavaScript engine pipeline from the V8 engine from Google. This diagram is a bit outdated because V8 moves really fast and they change these things basically every year, maybe more often. Nowadays, there is an additional optimizing compiler here. But I decided to include this diagram because it's really universal. It shows us how any JavaScript engine works, not only V8. It's split basically in three parts. There is the interpreter, the baseline compiler, and the optimizing compiler. In the input, we have the JavaScript source code, which goes through this pipeline in order to be executed. Usually, as I said, JavaScript engines are like very, very complex compilers. So in most modern JavaScript engines, those are embedded in the browsers. There are multiple layers of optimizations and compilers. It's not like just one pipeline that through which everything else goes. There are multiple layers that get invoked upon certain events or in certain scenarios. So this is very, very complex. So let's quickly go through the pipeline to get an idea of how actually JavaScript code will get processed and how it will get to actual execution. We start with inputting JavaScript code as a stream of ASCII bytes. It's basically a buffer with ASCII symbols that you put some JavaScript code into it. Our first stage is parsing and analysis. Actually, I bundled a few stages here for simplicity. What happens next is many things, actually. Your JavaScript code will be tokenized. Then it will be grammar checked. Syntax verification happens. Then abstract syntax tree will be built. On top of that abstract syntax tree, we will generate intermediate representation usually. And finally, on top of the intermediate representation, we generate bytecode. Bytecode is JavaScript code, which is already binary, except it doesn't execute directly on the CPU, but it will be interpreted later. Also, at this stage, there is some sort of additional runtime preparation, like variable allocation and setting up certain runtime structures to make everything work together. I will show you how the bytecode looks like in a moment. Here on the right side of the slide, there is the mnemonics that are used by V8 engine to represent V8's bytecodes. Here is how the abstract syntax tree looks like. It's from V8 documentation as well. From the source, the abstract syntax tree, it seems a little bit non-intuitive because it's not really, well, it's compiler theory. It's not like a common tree that you see in some diagrams. So I'm not going to explain it here. It represents each operation in the program as a separate node in the tree. And the children of those nodes are actually the arguments of the operation. You can see here some very common abbreviations such as LHS and RHS, which correspond to left-hand side and right-hand side. This is also compiler lingo, which means like a left-hand side of the expression and right-hand side, which happens when you, for example, assign a variable. The variable is on the left side and everything else is on the right side. This is very important for the parser. It uses a lot this kind of abbreviations. So if you're planning to look at the parser code, you will see a lot of this kind of compiler-specific lingo that you will need to be familiar with. So this is how the abstract syntax tree looks like. And now this is how JavaScript bytecode looks like. Now, look at the left side of the slide. I'm showing the JavaScript operation that I'm performing here is basically declaring a variable, new variable x, and assigns a simple integer value to it. And all this bytecode that you can see here, there is no filler. It's all meaningful. It all implements this very simple basic JavaScript operation. This is how complex it is. Every bytecode that you can see, in this screenshot, it's a dump from V8. It has both the bytecode mnemonics in the right-hand column, and it has the binary representation of the bytecode. This is kind of, it looks like assembly on the low level. So assembly is the mnemonic, and then you have the bytecodes. This is basically the same, except it doesn't execute immediately on the CPU, but rather it executes in the interpreter. So the bytecode then goes to the interpreter part of the pipeline. The interpreter is a piece of code which iterates through the bytecodes. And for each bytecode, there's like a big loop that iterates through bytecodes. And for each bytecode, it invokes a specific piece of code, which represents the related operations. Usually, this is a very large and complex piece of code because JavaScript language is kind of high level. It's not like in the assembly language. Aside from just executing this thing, the interpreter also will collect type feedback in order to know how to dynamically operate with types and how to optimize for them. But basically, this is the initial stage of execution in the JavaScript engine pipeline. It is very slow, and JavaScript engines always want to optimize and run faster. So at the first chance, the JavaScript engine will try to optimize the bytecode by lowering it. Lowering is a very simple process that you can think of as compilation. So instead of the bytecode, which is getting processed by the software that runs through the bytes, you now will have actual assembly code. So for each bytecode, there is a snippet of assembly code that will be put together to make a more low-level program. But at this stage, the lowered program is still rather slow because it's not optimized really. And finally, there is the optimization stage, which is where the most magic happens. Optimization stage is based on the classic compiler theory. There is a huge amount of various optimizations that can be done on the code. So to get an idea of what is an optimization, you know that in JavaScript, as a high-level developer, you don't care about types. You can take a variable and you can assign anything to it. And the engine just handles type translations underneath. And this is very slow because you can imagine that in the software level, all those translations are like very long, low-level code that compare what have you just done and what kind of type does it correspond to and how to handle that. So when we're optimizing, we translate the code into low-level assembly language, which assumes that this type is a specialized type. And this is where most bugs happen in JavaScript engines. Because if this assumption is wrong, then we immediately get some sort of memory corruption. So for instance, you optimize a function and somehow the engine believes that you are going to have an integer value in some variable. And then somehow you're tricked to believe that, and after optimization, somehow you trick it to accept a pointer value. This is where type confusion happens, and this is an immediately powerful primitive for exploiting the engine. So there is a lot of going on in the optimization stage. What you need to know here is that this is where the most bugs will be found. Here is a snippet from V8 code. You can see that there is a class named JS Native Context Specialization, which has functions starting with reduce prefix. It will actually, then there is a name of the bytecode. So the function will operate on each bytecode and it will try to reduce it to some optimized version of it. Usually this whole pipeline is not entirely linear. There are some loops and the engine will spin the same code multiple times. Most of it or some part of it will happen even in the background in modern engines, which is also an interesting source of bugs. And as soon as the engine recognizes that your function is getting hot or popular with the colors, it's called often, it means that it has to be optimized for better productivity, for better execution, and optimization will be applied to it. Now, the next part of the JavaScript pipeline, it's not really a pipeline, it's like subsystem in the code is where various runtime API lives. Here in this subsystem of runtime logic and API, you will find the actual JavaScript built-ins that you expect as a high-level developer, such as array, regexp, object, and so on. So usually the code which has been optimized, it will invoke those high-level APIs, and it will cause the engine to go out of the optimized mode sometimes and execute some high-level code. An important aspect of the engine is the actual basic primitives or basic concepts that it works on. Here is an example of how a JavaScript object looks like from the internals of the JavaScript engine. It's not visual. It can be visually represented as well. Here is just a dump from V8. And you can see that there is a lot of, it's a very complex structure with a lot going on inside of it. There is some map, there is a prototype, the elements, all of them have separate location and memory, as you can see. These are all the pointers. All of them are separately located in memory. There are also some additional properties or attributes assigned to this object. So there is a lot going on here, pointer to constructor and so on. So internally, a JavaScript object is a very complex structure, which is why we see so many memory corruption vulnerabilities, because there is just so much that can go wrong inside of this complex structure. So many things that can get corrupted and rather easily exploited. Now, another important part of this high-level big picture knowledge about JavaScript engines is the bug patterns. Each software has its own common bug patterns. If you think about things like there are buffer overflows, there are use after free bugs, type confusions, different kinds of vulnerabilities. They are not uniformly distributed in each software. So each software has its kind of preference towards a certain kind of bugs. And moreover, this preference will be changing with time. As security optimizations and hardening is applied, some bugs will be eliminated or bug classes and other bugs will appear. So JavaScript engines is not an exception. They have their own preferences for bug patterns. I start with uncommon bug for JavaScript engines. Your favorite classical buffer overflows and use after freeze are actually very uncommon for different reasons. I'm not going to dive deep into it here. It's very justified. It totally makes sense if you know how a JavaScript engine works. So pure buffer overflows are very rare, and use after freeze as well. Partly because the JavaScript engine is automatically garbage collected, so there is no this kind of edge cases as in other kinds of software written in C++. However, JavaScript engines have their own peculiar bug classes, even that are specialized to a specific engine. Like for V8, for instance, in V8 there are special bug classes, and in other engines as well. Now, for the common bug classes in JavaScript engine, the number one is type confusion. It happens really a lot because of the inherent dynamism and mutability of the underlying language structure. Because of the dynamic typing system, because of all these optimizations, type confusions is absolutely the number one vulnerability. Type confusion is a type of bug which happens when the code assumes a specific structure in memory, but it turns out to be a completely different structure. And normally in C++ code, you don't see this kind of bugs a lot, because if you want to convert a structure or a type, you do a static cast, for instance, or something like that, and it's immediately visible what you have done. It's really hard to make it a vulnerability in the code. But because in JavaScript engine, these things happen really deeper in the dynamically generated code. It's not so easy to see when your types are not compatible. So type confusion happens a lot. Another big class of bugs is vulnerabilities related to JavaScript side effects. This builds on the inherent property of JavaScript engine to be mutable and to support all sorts of callbacks. You know that JavaScript language supports callbacks natively. Like there are some built-ins that accept a callback function, but it's not just that. Actually, it goes much deeper in the JavaScript. Callbacks are everywhere. You can actually redefine something inside of the prototype chain, and your callback will be called implicitly when there is a prototype chain lookup, for instance. It will be completely hidden from the user, but it will be called. Or you can assign a callback when there is some type conversion. So if you try to assign a specific type to a variable, it will invoke a specific handler for the type. So there is a lot of handlers like this, and the basic meaning of this is that your C++ code or the runtime state of the engine will get interrupted and going back to the high-level JavaScript. And this is where a lot of bad things can happen when your code goes back to JavaScript. The whole structure of the program can be changed at that point. The types can be changed, the objects can be changed, everything. And when the code goes back to the C++, and it still assumes that it would see the same structure or the same kind of runtime situation, and that assumption will be broken. This is a huge class of bugs. It's not like a classical type of vulnerability. It's an umbrella term that I'm using here to represent different classes of bugs that follow the same pattern of causing various memory corruption or side effects through runtime reentrancy. Another big class of bugs is various optimization issues. This kind of overlaps with type confusions, but it doesn't have to. Optimization issues is all sorts of broken assumptions and security vulnerabilities that can appear during the optimization or inside of the optimized code. There are different things here. I'm going to skip it here. Most of it will be type confusion, as I explained previously, but also here may be a little bit more subtle or logic issues related to optimization. And the thing that I want to point out really is that the state-of-the-art vulnerabilities that are being found in JavaScript engines now are very complex. And even if you're a specialist in this kind of low-level code, you will not understand what the bug is about. And software developers themselves, they just don't understand what's going on. It happens just all the time. The bugs get reintroduced because developers applied a patch that is not working, because they have no idea what's going on here. It's, because this is one of the things that makes JavaScript engines really an interesting topic. Now with that knowledge, which hopefully it gives some basic idea of how JavaScript engines work, finally I will go through some specific technical examples of JavaScript engine bugs. So this is state-of-the-art talk, and I'm going to focus basically on two types of vulnerabilities that represent state-of-the-art. The most critical vulnerabilities, they are first vulnerabilities demonstrated at pound-to-on competitions, and second, in the wild exploits that were caught and reported to the vendor. Of course, there is a huge amount of other bugs found by security researchers that were reported, but usually the cutting edge of this whole vulnerability discovery is driven by in the wild exploits and competition exploits. So these are the two things that I look the most. Here is some list of vulnerabilities shown at pound-to-on in this year, only related to browsers. Not all of them are JavaScript engine. Some of them are inside the browser internals. Now, I kind of thought to cover the bugs here, but it's not realistic. There is too much going on here. So I'm going to cover just a few bugs that I looked at recently. Vulnerability number one. This is really recent. It's basically from last week. I published a blog about this, looking at the root cause. This was a vulnerability that was actively exploited in Google Chrome in this month. It was an exploit chain together with two bugs, the JavaScript engine bug and the Chrome sandbox escape bug. So I'm going to talk only on the first part, on the JavaScript engine bug. There is a link to the full blog. And here is the patch. This patch is remarkable for a few reasons. You can see that the patch is super simple. It is not so common in JavaScript engines and complex software to have this kind of trivial patches, like in old school buffer overflows, when we just add a check that some variable is under int max value or something like that. This kind of patch is just non-existent nowadays in the kind of complex and valuable software like browsers, JavaScript engines, or hypervisors. And here the patch is really simple, and yet, does it make sense to you? Even if I know JavaScript on the high level, and initially it wouldn't make sense to me at all. What is going on here? The patch is very trivial, and I have no idea. If you look closer at the patch on the right side, the only thing that is changed here is added a new check. Is JS object target? What exactly is this function? The set or copy data properties is basically some internal function in the engine, which performs the low-level copying of object data, all of its properties. This is used in several places. You can imagine if you're copying objects inside of your JavaScript environment, there are different scenarios where copying of objects can be invoked. And here is a snippet of the spec. Actually, these are some abstract operations from the specification that are not directly related to this bug. I'm showing this because it's kind of the same idea. The abstract operations in the spec define the set abstract operation on the object and a create data property. So this function is kind of send or copy data properties is kind of the same thing, but a little bit more high level. Internally, it those abstract operations. What we need to know is this function will be called anytime when in your engine environment you are copying object in specific scenarios. In the code, we can actually track it back to some specific. So when I'm analyzing the patch like that, I'm trying to think how do I actually reach the bug. This set or copy data properties. I can track this function backwards in the code and see where it's called from. In JavaScript engine, it's not trivial. And in many cases, the bug is really hard to reverse engineer or not even possible. But here it's more or less approachable. So by tracking back this function, I go back to certain runtimes, like runtime function set data properties and copy data properties that use underneath this function. And then I go back to the object assign high-level built-in that you can actually call from within JavaScript environment. This is how you can reach the bug, by calling object assign and doing something with it. So with that knowledge, we can look at the patch again and try to make sense of it. Here, there is some sort of check which checks our target. You know, if you consider, for instance, the object assign, it has some arguments. It has the source and the target object. The source object from which the properties will be copied and the target object. So here in the code, we can see the target object is being checked for some sort of properties. Originally, it has checked whether it's JS global proxy or not, whether it does have or not the fast properties. This is all related to how the object is internally structured in the engine. And in the patch, a new check is added, whether or not it is JavaScript object. So what's going on here? We can actually look at the proof of concept for this, created by the security researcher with this really hard handle. I have no idea how to pronounce it, so I will not, sorry, but so here it is a snippet of the proof of concept. I skipped the part which creates a WebAssembly module. It was above. Then there is something going on, and finally we call object assign with an array 42 as a target. Array 42 is actually it's a WASM array here. So this is starting to make sense, because looking back at the patch, the target. So now we can see what's wrong in the patch. The original code assumed that our target is a JavaScript object structure type, but it turns out that it's a WASM type, which is a completely different structure on the low level. It's a different memory structure. So the check ensures that the object is strictly JavaScript object. We can see how it works out in the proof of concept. Because originally the code assumed that this first argument would be a normal JavaScript object, which has a certain internal layout structure. And here it is a WASM array object, which has a totally different internal structure. So this function will be copying some data, assuming a totally different structure. This is where memory corruption happens, and it's turned out to be exploitable. This is so this bug, for some reason, it wasn't announced like a type confusion. It was announced like out of bounds write. But in my opinion, it's absolutely type confusion, classical one. And here is how it looks when the bug is triggered. It's the crash. It's ends with abort, so it's not really a pure crash, so to say, but it was caught by the debug environment inside the V8. It's a very common thing to see this kind of crash logs if you're fuzzing JavaScript engine or triggering a bug. So the first thing that stands out here is you get a lot of this kind of blank spaces here with question marks, which means that there is no symbolic information available. It happens a lot, and normally JavaScript engine stack trace will look even uglier than that. There will be a lot of like this kind of question marks intertwining with normal symbolized data like here. This is because JavaScript engine, as soon as when it's executing the interpreted code, you can guess that it cannot be shown directly in the stack trace because it happens in the state. And then when lowering happens, the JIT optimized code doesn't have symbols as well. So inside the stack traces, you will see a lot of this kind of blank spaces. And then we can see inside of this trace what's going on. Here is our runtime set data properties function, which was vulnerable. From there, it gets to the branch that I mentioned previously, where there was a check if the object is JavaScript object or not. It then goes to normalize properties, which is the function that uses a lot of low-level operations to copy data, which is where the actual memory corruption happens. Then at this stage, there is some map normalization, and finally we hit an abort. So in this situation, the crash was kind of caught with debug environment, but normally it will be a memory corruption. There, somebody already developed an exploit. I didn't debug it yet, so I cannot walk through it. Here is the link in case you want to see it. I kind of get the overall sense of what's going on here, but I cannot explain the details at this point. So another example, this is a vulnerability. This is not an in the wild actively exploited bug, but rather it was demonstrated at Pound-on competition, one of those bugs. If you look at the patch, it says that the DOM array buffer was maintaining its own detached state and would consider itself non-detached even if the corresponding array buffer was detached. So because I really have a lot of knowledge about previously found vulnerabilities in JavaScript engines and in other software as well, then it immediately connects for me that it is array neutering bug. You remember that in some of the previous slides, I mentioned that array neutering bugs kind of is supposed to be gone at this point because it was a very simple bug class. But here it just happened and it was exploited at a competition, which I think is remarkable. So I'm not going to explain what is array neutering. You can look it up, I think. Basically, it produces one of the rare kinds of use after free in a JavaScript engine. And here is what happened here. This is what the patch looks like. It's part of the patch which is the most relevant, which adds some logic related to checking whether or not the array was neutered. And here it's related to DOM, to document object model. So probably it was introduced more or less recently, which is why the bug was found in the first place. Another example that I will just mention it here is another vulnerability from Pound-on competition found by Manfred Paul. This one is really interesting. It's also related to WebAssembly a little bit, even to more extent than the first bug that I discussed. Here is the snippet of code, which is relevant here. The vulnerability here happens in the parsing of the WASM module, specifically the type section, which compares that the amount of WebAssembly types in some structure is below a maximal allowed value. And what happened here is that at some point additional code was added, which introduced recursive types. So this check wasn't enough anymore, and it was able to be bypassed. And once it is bypassed, it's possible to corrupt memory and create a universal type confusion primitive with it. This is a very interesting vulnerability, and it's actually the blog explains it better, which is linked here. I recommend to read it. And also, it kind of shows in a universal way how type confusions are exploited in JavaScript. I have at some point published an exploit and a blog about exploiting JavaScript engine type confusions. I think it's quite good to understand the basic fundamental level of it because it's quite approachable. it's easier than most type confusions that you can find nowadays. So you can find it on my website and on my GitHub to look further into it. On this slide, I'm showing different parts of the exploit and how it all works together, basically. Starting from the vulnerability in type confusion to building primitives and different stages of the shell code on the assembly level. I think this really helps to understand the fundamental level of how type confusions are exploited. And because this is such an important type of vulnerability, it's one of the first things that you want to learn about if you want to research JavaScript engines. And my last mention, this is just from today. Guys started sending me this the link to the patch, this new vulnerability that was just recently patched by Google as another actively exploited vulnerability against Chrome browser. So what's going on here? In last year at Positive Hack Days, I presented my analysis of this vulnerability number 4262. It was a very interesting bug in the parser subsystem. You can find, I've linked my video talk here. There is a link to watch it. And it was a bug related to parsing and scoping various things inside of the runtime. It's very interesting. The exploit is not trivial as well. After my initial, so when I did this presentation, there was no information about this vulnerability. Later, community researchers and my colleagues started to look into it. They have published a proof of concept, and they even published exploit, which is not trivial, very interesting. And now, then this new bug that just appeared a couple of days ago, it basically logically in the same attack surface, so to say. It's not related to arrow functions and escapes, I think. It does have the same logic around it related to parsing and expression scopes. So this is very interesting. I haven't looked into it deep yet. I just recognize that it's basically along the same lines. So this is, I think there will be more information published soon about this one. So I just leave it here as introduction. That's all for today. Here I'm linking a few references to ECMA specification and the book for compilers that I mentioned previously. My YouTube channel, where you can find the talks related to it, to JavaScript engines and other topics as well. And the link to my blog, where I posted some blogs on the related topics. Now is the time for questions.
Hello. Thank you, Alisa, for a wonderful talk. Do we have any questions from the audiences? Okay.
Thanks a lot for your talk. I have several questions. First, what do you think about, when you told about type confusion bugs, I thought about hardware mitigations which can solve them for operating systems. For example, it is memory tagging in ARM, MTE, or pointer authentication. Because when you have pointer to an object, you can have a tag which describes the type of the object. So it looks like it can help. What do you think about that?
Exploit mitigations for JavaScript engines is a hard topic, because you see the nature of JavaScript engine is that it's really dynamic, and it executes this. It needs to emit low-level code and then execute it. It means that majority of exploit mitigations are actually irrelevant to JavaScript engines, like CFG, for instance. When people talk about common mitigations, they relate to C++ code, but in JavaScript engine, you just easily bypass it. So basically the same thing with this pointer authentication. And also the same reason why we cannot just throw Rust at JavaScript engine and make it secure, because Rust doesn't support kind of low-level code generation. So because of that, JavaScript engines are kind of immune to any sort of low-level exploit mitigations that we have seen so far.
Nice. Thanks for the answer. Another question. You speak about systems which are so complex that it looks like at some point it would be not possible for a single person to understand its security vulnerabilities and so on. And what do you think? Can computers help us to learn and save us from losing the out-of-date knowledge about those systems? Because sometimes it feels like very difficult to keep up with all of this new knowledge which appears.
Yes, totally meaningful question. And actually, this kind of dynamic development of JavaScript engine is part of what makes it interesting. Not just as a good sport, but also because it moves fast. So it kind of, if you have what it takes to go after it, then you don't have competition. That is the positive side of it, okay? But also there is the negative side. As you say, it's very hard to catch up with it. And it gets hard even at the point when you start to contain all the system in your head. It doesn't really have to be fast moving. So, and this is actually a very common question that people ask how to get around it. So in my work, I use a few approaches to tackle this. I'm going to just mention one. It's very simple, is to try to look deeper and focus on the core, of how it works. See, if you know how it works on the core, you can predict where the high-level concepts will go next, if that makes sense. And you know that the high-level concepts will keep moving. There will be something added to the specification, new code is added, but you know how it works deep internally, and you just expect that it will be there. Mm-hmm. This is basically how my training system is structured. Honestly, is based on this one principle, that we want to learn the core because we don't want to run after all these changes every day. Like what the new code added, the new specifications, the new mitigations. Just focus on the core and be able to predict the high-level things and the fast-moving things. That's the principle.
Nice. So you just learn the principle and drop the details and it's okay?
No, absolutely not. I mean that my main focus is the core because it kind of gives the most control and the most knowledge about the system, the most predictability. I absolutely do not drop. As you can see, I publish ZeroDay insights systematically on my blog. I look after all the bugs that appear, all the new exploits, the new code that was added. There is a lot to track. There are other aspects. There is actually quite a lot of things that you have to learn to actually make it work. Basically, I would say that it's possible to optimize your brain in such a way that it is not difficult to follow these things. Once you have the core fundamental knowledge and you have the kind of optimized approach to processing the new things that are incoming, it's faster than you think and it's easier than you think. It's already a different domain. It's in the domain of cognitive optimization. So it's kind of a bit different topic and I can talk about it indefinitely. So I hope I answered the question.
Nice, thanks. Last short philosophical question. Do you think that it is from the first part of your talk? Do you think that security research is for everybody or it is for special people with special features of the brain?
I'd say that it is definitely not for everybody just because everybody is different, but I wouldn't say that it kind of requires any special, genius or elitism or anything. It's just that also from the diagram that I showed about the cybersecurity industry, there are different things that is going on here and different people can find their place inside of it. So not everybody will go after vulnerability research after all, for different reasons. For some of them, it's just not interesting. For some of them, it's not the thing. Maybe it's not exciting. For me, it's definitely the best. And I'll be honest. When it comes to really being at the top of the industry and catching up with the most recent things, definitely it takes a lot. Maybe not even so much some intrinsic properties as readiness to work hard, to work more than the others, to apply yourself, to look deeper. It does require a certain amount of IQ. I wouldn't say like specifically like you need to be super smart, but I would say that the most important thing is actually perseverance, persistence, and the readiness to work hard and to being able to analyze the systems. That is the basic of it, I think.
All right. Do we have any other questions from the audience? No. Okay. So thank you very much. Please give a big round of applause.
Thank you.